In this video, we'll be taking a look at cache. The basic idea behind cache is that the processor's clock frequency is a lot higher than main memory. And so whenever the processor has to write to memory or retrieve something from memory, it ends up sitting idle most of the time. And so what people came up with is that on the actual processor chip, we could just have a little amount of memory, and whenever the processor needs to access memory, it could access it from there instead of having to go out to main memory. Now at first this might seem like it doesn't work, but thanks to spatial locality and temporal locality, the information or data we're looking for in the cache will actually be there 90% of the time. And so suppose that we have this loop right here, and this is our, let's try that again. That is not much better. All right, that'll have to do. So let's say this is memory, right? And so we're defining a variable here. So somewhere in memory, we're going to have the variable sum. And then we also have the variable I, which is somewhere else in memory. It doesn't necessarily have to be next to sum. And then we also have an array, right? So somewhere the start of the array will be here, and then maybe the last element will be down here. And so temporal locality says that if you access an address, then you're likely to access that address again soon. And so if we look at this loop right here, we can see that for every iteration of the loop, we access some here, and we access some here. So here we're reading some, and then here we're writing to it. And if we look at the variable I, well, every single iteration we're going to increment the value of I, and then we're going to check if it's smaller than some other value. Okay, so that's temporal locality. Spatial locality says that if you access an address, then you're likely to access an address close to it soon. And so you can see for every iteration of the loop, we accessed the next element of the array. And so these were presumably all right next to each other in memory. And so going back to our example here, theoretically, if we had the data corresponding to all these addresses in our cache, well then we could run this loop without ever having to go out to memory. Let's take a look at a direct map cache. The way a direct map cache works is that your main memory is going to be greater than the cache size. And because of that, we need to find a way to map addresses to specific locations in the cache. And the way to do that in direct map is that we will take the address. So let's take the address 00001, and we take the modulo of the number of blocks in the cache. So here we have 8 blocks, and so the 1 modulo 8 is just 1. And so this location right here would map to this location in the cache. I didn't draw it here, but let's say we had location or address 2. The modulo of that would be 2, and so that would map to this location right here. Now, let's take a look at another number. So let's look at 9. So 9 modulo 8 is actually 1 again. And so this address maps to this location. 17 again will map to the same location in cache, which is 1. And so in the event this happens, we'll end up having to swap out the address. Forgive me for my poor drawing skills, but this should be good enough to get it done. So let's say the processor needs to access a specific location in memory, and so they have a 32-bit address. The address is actually going to be interpreted differently by the cache. And so the least significant bits are going to be used for the offset. And the offset allows you to access every byte within the data. So let's say the data we're working with here is 32 bits long. Well, then that would be 4 bytes. 4 bytes is 2 to the 2. And so we would have 2 bytes as our offset. So enough to select every byte within our data. Now, the next field is determined by the size of our cache. And so if we had a 1 kilobyte cache, that's equivalent to 2 to the 10. And so we would have 1024 different locations in our cache. And to reference every single one of those locations, we would need 10 bits. And so our index is going to be 10 bits. And so to determine the tag, we just take 32 minus the index and then minus the offset, which gives us 20 bits for the tag. And recall how in a direct map cache, 2 addresses in main memory, so let's say 1 and let's say 9. I know this cache size is bigger, there's more blocks, but let's go back to our example of 8. Well, then these would end up in the same location in cache, so they would actually be competing for this spot. And so we use the tag bits to distinguish between the two. And obviously, right, if this were longer, right, it would be 32 bits long, so we would look at the first 20 bits, and if the first 20 bits corresponded to this one address right here, well then this right here would be on, or true, or 1, and valid bit I'm going to get into in a second, but that would be considered a hit. And so what the valid bit is that so RAM, random access memory, is volatile, which means that when you turn your computer off, all the data in it is lost. And so when you first boot up your computer, there actually isn't anything in RAM. But let's say that the cache in the tag field right here, let's say it was set to all zeros. Well, the computer might think that the data right here is the data that corresponds to the data at location 0. But in reality, this is garbage. We don't know what this is. It could be all zeros, but it might not be the content of that address. And so we initially will set all the valid bits to 0. And then when your computer first boots up, obviously it's gonna miss a lot, and whenever it misses and it fills in this field, it's gonna set the valid bit to 1.